So welcome everybody. This is a really, really great time. I'm excited to introduce our speakers. Usually we have somebody come in from outside, but now we have two students from SUNY New Paltz who spent the summer working on research projects, and they're going to tell us about those research projects. First up, we have Phoebe Heretz, who spent the summer at the Harvard Smithsonian Center for Astrophysics in Cambridge, Massachusetts. Phoebe's a senior. She'll be graduating soon. Phoebe, actually, this is her second degree. First is in music, I believe, right? And when I first met Phoebe, it turns out we ended up talking about model solar systems because she had set one up on the rail trail over on Ulster County. And as everybody in the club knows, I set one up on the walkway over the Hudson. We joined forces and she's helped me set this up several times. So she's a very active student in our department. And what else I should tell you that last summer, she spent the summer doing research with James Webb Telescope data at Vassar. So Phoebe, welcome, and we're looking forward to hearing about your summer.
Thank you so much. Thank you so much for the introduction, Dr. Myers. My name is Phoebe. I study physics and astronomy here at SUNY New Paltz. But this summer, I was at the CFA studying galaxy evolution. And what we're looking for is a new way to study the enrichment of galaxies across the universe. Dr. Myers, do you mind giving me 5?
Sure.
So before we begin, I'll describe what metallicity is and why we're interested in studying it. In astronomy, metallicity is considered the abundance of elements heavier than hydrogen and helium. We now know that hydrogen and helium were fused shortly after the Big Bang, but everything else is formed in stellar lives and deaths. So here we see the periodic table split out by the sources of the elements. And you can see in blue, hydrogen and helium and a little bit of lithium were formed by the Big Bang, but mostly everything else was formed in stellar processes. Okay.
Why is it doing that?
What? Oh.
Okay. So we can see the rest of the Big Bang, the rest of the periodic table is created by things like exploding massive stars in yellow. In purple, we have merging neutron stars. So, and here we have a supernova remnant. So this is a massive star that has exploded, and in that explosive process has fused these elements that we see in the colors here. So therefore, if we can measure the metallicity or the richness of these heavier elements in these galaxies, it gives us a sense of galaxy evolution because it gives us a sense of how many generations of stars have gone through and enriched the gases in the galaxy with these heavier elements. And so this is particularly interesting in the time of the James Webb Space Telescope because we're finally able to observe some of the earliest and youngest galaxies. And so it's especially crucial to study how enriched they are. So how do we measure metallicity? We use what we call a spectrum. So we take the in-source light, or the source light from the galaxy, and we split it out through something like a prism, and we split out all of its colors or component wavelengths into what we call a spectrum. And that's what we see in the colors above. And then if we kind of flip it on its side, we can get this intensity map with wavelengths. And so you can learn a lot from spectra. So here we have a very high resolution, clear spectrum from the Sloan Digital Sky Survey. And you can learn so much from spectra. So you might notice here, there are species of elements that are labeled. So we have hydrogen alpha and nitrogen 2. These are ionized species of the elements. We have oxygen around, sulfur. So you can learn a lot from these rich spectra of galaxies. So more specifically, we measure metallicity by looking at oxygen in galaxies. And the most direct way to do this is with this oxygen 4363 line. It's what we call an auroral line, and it's temperature sensitive. And it's found in these H2 regions in galaxies. Specifically, H2 regions are star-forming regions where young, hot stars are ionizing the surrounding hydrogen gas. And so we're looking for the oxygen abundance in these H2 regions. We also look at oxygen because it's the most abundant of these metals. And it's the units of metallicity. I just want to point them out here. They're a little strange. The 12 is from the magnitude of the least common metal, which is uranium in this case. So that makes metallicity, or Z, always positive. Oh, that's what it said. But these auroral lines, this most direct method, is weak and it's difficult to detect. So researchers had to develop a new method to measure metallicity. So what they came up with is what we call strong line metallicity diagnostics. And that's what we're looking for in this study. And instead of this auroral line, they use ratios of strong emission lines readily available in galactic spectra. And what they're looking for is these trends like we see here. So we have metallicity on the x-axis. We have the ratios of emission lines on the y. And we're looking for these relatively one-to-one, relatively steep slope trends with not too much dependence on ionization, which is the colored lines. So these have been studied in the UV range, the visible range or the optical, and the infrared range. And the purpose of this study is to find a diagnostic in the optical that we can use for low redshift or local galaxies to high redshift distant galaxies that are stretched into the infrared. And another goal of our study is to find one of these diagnostics that we can use for low resolution spectra. So the SDSS galaxy or spectra that I showed before is very high resolution, but that's difficult to achieve depending on the instrument or the amount of time you have or how far away the galaxy is. So we want to find a diagnostic that we can use for low resolution spectra like we see on the right here. So you can see now this H alpha and N2 line, which was they're very close in the high resolution spectrum, but now they're blended. They're now inseparable from each other. So this is what we mean by low resolution. And so some example use cases of this, we hope to apply this diagnostic to low resolution surveys from JWST's NIRISS or the upcoming Euclid and Nancy Roman observatories, or for this instrument on the Hubble Space Telescope that I'm showing here. So these are some example use cases of this low resolution diagnostic. And lastly, we're interested in star-forming galaxies. So I'm referring to galaxies where the dominant ionization or excitation source are these young, hot stars. Go ahead. Sure, of course. Oh, thank you.
Go ahead.
So conversely, another common ionization source are AGN, or active galactic nuclei. So what I'm showing here is another diagnostic tool that we use using the strong emission lines in galaxies. This is called the BPT diagram that separates the galaxies by their dominant ionization source. So we are interested in the green branch, which is the star-forming branch, and we're not as interested in the AGN branch. So I'll briefly mention, these are some separating lines. We have the Kaufman line. Everything below that is considered a star-forming galaxy. Everything above is considered an AGN, or sorry, everything above the Keeley line is considered an AGN. And everything in the middle is what we call the mixing sequence. Go ahead. Oh, sorry about that. AGN are active galactic nuclei. So they're the large supermassive black holes at the center of galaxies that are very active at the time. So the dominant ionization source in those galaxies comes from the very active black holes at the center. So for our use case, we looked for new trends, one of these new diagnostics, using the Sloan Digital Sky Survey, which is a survey taken at the Apache Observatory in New Mexico on this 2.5 meter telescope here. And the Sloan Digital Sky Survey is prolific. It's considered the most robust and complete optical survey of the local universe. There's about 1 million galaxies in its survey. And so we honed in on that very large data set by only defining the star-forming galaxies below the Kaufman line. And we selected very local, low redshift galaxies with a high signal to noise, so that's a strong spectra. And that left us with about 150,000 galaxies to work with. And these are the specific emission lines and the species that we are interested in looking for, or looking for trends with. And in the end, I tried out many different combinations of these emission lines and ratios with each other. And so here we present the strongest candidate diagnostic. And this is using that H alpha and N2 blended line over the oxygen 3 line. And so it has what we're looking for. If we refer back to the diagnostic panel I showed at the beginning, it has a monotonic trend with a relatively steep slope, and it doesn't present too much scatter, but I'll get to that in a moment. Another promising feature of this diagnostic is that these emission lines are really strong, they're really bright in many galaxies, and they're readily available. So a key feature of extragalactic astronomy is dust. Dust is crucial to correct for when we study galaxies. So we understand the dust in the Milky Way pretty well, but then we have to correct for the dust in the galaxy that we're observing as well. And this panel shows how dust can impact the intrinsic light from the galaxy. So we can see it can really darken the intrinsic light coming to us. So it's crucial to correct for it so we truly understand what's going on in the galaxy. But it's very difficult. This is still an ongoing challenge in astronomy. So what we used for these very high resolution SDSS galaxies was the Balmer decrement, and that is the most robust method we have for dust correction. But as you can see, it uses H alpha by itself. So it would not be usable for these low resolution spectra where H alpha is blended with N2. But anyways, for the STS galaxies, we're able to use it. And with it, we're able to calculate color excess and finally the intrinsic flux coming from the galaxies. And what we find is what we were hoping for, and that is there is a small dust dependence at high metallicities, but there is relatively little dust dependence at lower metallicities. So this is what we were hoping for because it will be so difficult to correct for dust with these low resolution spectra. So this was also an exciting result of our study. And lastly, we wanted to compare our data analysis. Oh, I also wanted to mention each of these very fine dots is a galaxy. I wanted to mention that before if that was unclear. So we wanted to compare our analytical data analysis or our data analysis with some theory. So we use what we call stellar population models. We put those through, they spit out stellar spectra. Then we put those through another photoionization model. And that photoionization model, which we call mappings, then spits out these theoretical diagnostics. So these are the results of the theoretical study. And this shows us ionization dependence. So as I mentioned earlier, we can think of ionization as the excitation sources in these galaxies. So the greater the ionization, the greater excitement of the atoms and molecules around. So what we see here is that this trend theoretically should have a low ionization towards the top, shifting towards a high ionization at the bottom. And our STS galaxies all fall within a similar range of an ionization parameter of about 7.5, which makes sense because they're very similar galaxies with each other. They're all star-forming galaxies. They're all very local. So we expect that they should have a similar ionization. But then what's also compelling about this result is that the ionization dependence is mostly at lower ionization and becomes less dependent at high ionization. And this is crucial when we want to study higher redshift or more distant galaxies. And this is because we're in a relatively quiet time in the universe. And so as we go back in time or more distant, higher redshift, star formation was peaking. This is a graph of essentially of star formation over cosmic time. So we're in this relatively quiet time now, but at a time about 10 billion years ago, corresponding to redshift 2, star formation was peaking. So it's incredibly highly ionized environment. And this is what we call cosmic noon. So we can assume that if we want to study these higher redshift galaxies, they will be more ionized. So we can study things like star formation rate or other ionization tracers if we want to understand the redshift dependence on our trend. So going back to our model, so we can assume that this low to high trend corresponds to ionization as well as redshift. And we do have preliminary results of high redshift data that does fall below the SDSS galaxies as expected. And here's some preliminary work using the SDSS data. And this is using an ionization tracer, which is the O3 over O2 line. And we can see it is behaving as we expect. Low ionization is in the cream colored and then high ionization in the dark colors. And so we're gonna test this out with high redshift data from the MOS-DEF survey using Keck. and then higher redshift SDSS data as well. And then finally, once we're done analyzing the dust and redshift dependence, we're going to try out our diagnostic to see if it's working well. We're going to try it on this low resolution Hubble data that I showed in the beginning. And then from here, we're interested in calibrating this diagnostic for even higher redshifts. So for now, we're going to calibrate up to cosmic noon. But what's so compelling about these emission lines is that they're essentially bright across the observable universe. So in theory, this diagnostic could be used for local galaxies all the way to essentially the edge of the observable universe. So I'll explain this further. This is a panel from the NIRISS instrument on JWST. On the x-axis, we have rest wavelength. On the y, we have redshift. So with redshift 0 corresponding to local, redshift 12 being very, very far away. So redshift 2 is 10 billion years ago. So it kind of exponentially curves out or evens out, decays at my brain right now. But we can see labeled here are the emission lines that we're looking at, and they are the most bright lines across all of that time. So in conclusion, we recommend this diagnostic for low resolution spectra when previously known diagnostics are not available. And here again are some of the use cases for this diagnostic. And we hope to use this diagnostic for star-forming galaxies or galaxies dominated by young hot stars, all within a similar parameter space, which will limit any dust, ionization, or redshift dependence. And I just want to give a shout out to my intern cohort this summer. I had a wonderful time at the Center for Astrophysics. And I continue to do research there, and I'm just so grateful for this experience. And thank you for having me back. I was here in the spring talking about protoplanetary disks. And at the time I was like, I'm gonna apply to RUs again, fingers crossed. And I ended up getting, oh my God, sorry, my dream internship. So it all worked out. Thank you.
Do we have any questions? Scott?
Yeah, once you sorted all the galaxies in that you know by you've discovered but basically you've whittled down the number of galaxies, and you settled on, okay, these galaxies are the ones that we're looking for. What do you do with that data? What now? What is the use of all the categorization?
Sure. So are you referring to, so we kind of defined our data by that star forming
Right,
branch?
exactly. So now what do you do with, what does that tell you?
Sure. So star forming galaxies and AGN, or the active galactic nuclei, they behave very differently. So researchers generally treat them separately when they do, especially with diagnostics like this. So we can't bucket them all together because they are such different beasts when it comes to what we learn from their emission spectra. Does that answer your question? Or are you wondering how the diagnostic came to be from the galaxies?
No, I guess, let's say, all right, so that this galaxy is an AGN, but this is, this other galaxy is the one you're looking for. It's the You know, it's a star forming galaxy. Just knowing that about the galaxy, how does that help researchers learn more? What are they looking for essentially, other than just the fact that it's a star forming galaxy?
Sure. I guess so. Star formation is so AGN. So galaxies dominated by AGN. That's kind of all you can see in them. It's like just it kind of like blows out
Right.
the spectrum. So
Right.
if you can define the star forming galaxies, there's a lot of interesting things you can learn in star forming regions. And it's compelling to see how those evolve over time, because like what I showed with the peak star formation graph,
Mhm.
like it's that kind of information we can learn. And when it comes to metallicity, that information comes from stars. So we want to understand the star forming regions better, how they evolve across cosmic time. So it's
Yeah.
good to hone in on those ones that
Right.
we can read essentially.
Does it help find population 3?
So that's exciting. So population 3 are the purest of the stars that we haven't been able to detect yet, but in theory, they should just have hydrogen and helium from the Big Bang and none of the metals that are formed in their lives and deaths. So those haven't been discovered yet, but that's a tangential part of the study, and we hope to find them with JWST. Yeah.
Okay, yeah.
Pass it back.
Well, so,
Next. Is that a question?
Yeah, when you
It's just so that people.
yeah, when
online
you
can-
when you're do you use infrared infrared telescopes, or do you use just like optical telescopes and then you break the light down that way, or how's it done?
Yeah. So what's good about using an optical spectrum to do this analysis is it can be used locally, but then as we go more distant in the universe, that light gets stretched by cosmic expansion,
Okay.
and then it gets stretched into the infrared.
Okay.
So building a diagnostic in optical can be used with optical observations of the local universe, and then infrared observations like with JWST in the distant universe.
Perfect. Thank you.
Anybody else? Jeremy. You gonna give her a hard time? They know each other.
So you said redshift 2 is 10 billion
Yeah.
years? And so actually no, that or yeah, I guess. Oh, okay, 10 billion. So redshift 12 is how many?
It's pretty much the edge.
The edge of
Yeah, of
Pers-
the observable universe.
observable universe.
Yeah.
Wow. So like the Big Bang, basically.
The like radiation from it. Yeah.
Okay.
Pretty close.
So on the other graph,
This one?
the one towards the end,
Oh,
yeah, that one. Why is that line
cut off.
lighter? It's lighter towards like closer towards our closer universe, right? Like sorry, closer to us. Yeah, there. Like why those lines are so much lighter there.
Like dimmer.
Yeah, dimmer. Yeah, sorry, that's what I meant. Yeah.
I guess
dimmer.
that's a compelling result with these emission lines, because it could be telling us that they do get stronger with cosmic time, which would be even better for our diagnostic. The reason we can't apply our current redshift calibration techniques to the high redshift is because N2, so we can assume metallicity will be low in the early universe before many stars had gone around and populated galaxies with heavier metals. So we don't want to assume that the same conditions will be around in the early universe. So in particular N2. But otherwise, so it's probably H alpha dominates. O3 becomes brighter with low metallicity. So this makes sense as we see it here. But it could be, it's a promising sign about the diagnostic. Yeah.
I have a related question
Sure.
back on that graph. You mentioned, what is it? Cosmological noon or cosmic,
Cosmic noon?
cosmic noon
Yeah.
at either redshift 2 or 10 gigayears look back.
Yeah.
Is that just because the curve, now what's plotted on the vertical here?
It's
I can-
essentially star formation rate.
Star
Yeah.
formation rate. So
Yeah.
you're calling noon when is this analogous to the sun going up and coming back down in the sky?
Probably.
Oh.
Oof.
Okay,
That's cool.
that's the curve. That complicated curve is just, oh, look, it's like the sun going up and that's noon.
Pretty much. Yeah.
Okay,
I
funny.
like that.
haha, get it. I get it now. So
I like that.
anybody else? We thank our speaker again.